Okay, so good morning, everyone. So first, I'd like to begin by thanking the organizers for arranging this very nice meeting, and also thanks to them for inviting me to present some of our recent work here. So, I'll talk about certain interesting quantum many-body scars that arise in a particular model, and yeah, so these are my collaborators here. I would like to acknowledge all of them before I start explaining the main part of the talk. Most of this work was started by discussing with my colleague Debashish Banerjee in a neighboring institute in Kolkata, the Saha Institute of Nuclear Physics. And then there was some contribution by Saptarshi Biswas, who was a master's student at IISER Kolkata. And then the rest of the things were done by Paolo, but mainly Indrajit Sau, who's a very good graduate student in my group, and he's also part of this conference. So if you're interested about various aspects of this work, you can either catch me or catch him. That's better to learn more about it. Okay, so, right, and these are some of the references. I'll also put up slides for one or two unpublished things, just to get some feedback from some of you who may have more intuition about these things than me, but okay. Good, so the central question that many of us sort of think about is, how do macroscopic quantum systems self-thermalize? So basically, imagine that you have some, let's say, spin model with a short-range Hamiltonian on a lattice, and you initialize it on with some simple initial state, which you can prepare in a lab, let's say, okay? And then you just let it go. Right? So this is perfectly unitary evolution. And then, of course, the paradox is that unitary evolution cannot erase quantum information. But the key point is that if you look at only local operators and their time evolution, then because of the way quantum entanglement propagates in real time, actually the memory of the initial state, apart from some global conservation laws, is quickly transferred to highly non-local operators, and effectively the system thermalizes, right? Even though this is a perfectly unitary evolution. So this is an example of that. This is some actual calculation on some 1D spin chain, where you look at a local spin operator. And of course, you can see that there's an initial transient, but then the system seems to relax to some quote unquote thermal value, right? So that's the hallmark of thermalization. And another way to say all this is that there is this eigenstate thermalization hypothesis, which is actually, in my opinion, the only good definition of quantum chaos, but we can debate about that offline. Basically what happens here is that many-body eigenstates of local Hamiltonians, which have a finite energy density, they appear to be thermal for all local operators, where the temperature is basically set by the energy density of the eigenstate that you're looking at, okay? And so that's very important. And okay, that wasn't me. Okay, good. Right, so this eigenstate thermalization hypothesis seems to be a very super universal thing. Any sufficiently complicated quantum system which is not integrable should satisfy this. But in recent times, we have seen surprises here. Okay, so one of the key experiments which actually led to several developments in this field was an experiment carried out in Misha Lukin's lab at Harvard, where basically they could engineer a system of 51 qubits. There were 51 Rydberg atoms, and you can imagine it as a two-state system with a Rydberg ground state and a Rydberg highly excited state. Okay, so it's like a spin-half interacting theory. And because it's a 51 qubit system, the Hilbert space available to you is rather large. Okay, and you would therefore expect that if you start with the initial state and you just let it go, it'll thermalize. Okay, but to their surprise and to everyone else's surprise, they found out that certain initial states took very long to thermalize. Okay, in fact, they showed some anomalous oscillations remnant of block oscillations, even though block oscillations is a property of few body quantum mechanics, not of many body quantum mechanics. So in particular, in their experiment, when they started with this state, so as I said, this is like a two-state system. So you can always initialize things by 1 and 0. So 1 is like a Rydberg excitation, and 0 is like a Rydberg vacuum on a particular atom. So if they start with the state 1, 0, 1, 0, 1, 0, and so on, so that's a very ordered state. And if you are a quantum magnetism person, it's like a nail state, right? So if you start with this kind of a state, it seems to show some interesting oscillations and go to its partner 0, 1, 0, 1, 0, 1, which is just a translationally shifted copy of this, and again back to 1, 0, 1, 0, 1, 0, and so on. Okay. Whereas if you start with a state which has all zeros, which is all Rydberg vacuum at each of the atoms, then basically this state, which shares the same energy density as that state, in fact rapidly thermalizes. So this is what you expect from ETH, this rapid thermalization, and this is what you don't expect from ETH, right? And so this is like weak ergodicity breaking, where most initial states seem to happily thermalize, whereas some particular initial states, which are simple to create in a lab, don't seem to thermalize, okay? And soon after the experiment, this was understood in a set of rather beautiful papers, which I'll come to soon. But this model has an interesting history. This PXP model was sort of the minimal model for the experiments. So it appeared in the literature actually several years back. And one of the first papers where it appeared had a chairman contributing to it. Okay, so, but anyway, the model is the following. So imagine you have L spin half degrees of freedom on a 1D lattice. Now, the key point to realize when you try to model the experiment is that these are Rydberg atoms. So if two atoms are in the Rydberg excited state, that actually requires a very high energy cost. Okay, so to incorporate that in a model, in a first approximation, you just say that two up spins, if they are neighbors of each other, are disallowed from your configuration space. Okay, so these two guys are disallowed if they are nearest neighbors of each other. But this is allowed, and this is allowed. So this is a constrained Hilbert space, and so all the 2 raised to the power L configurations are not allowed to you. And it's a simple counting exercise to show that actually the dimension of the Hilbert space grows like this. You just need to write a 2 cross 2 transfer matrix and it comes out. Okay, so it scales interestingly like the golden mean raised to the power L, if L is large enough, and not as 2 raised to the power L. So now what is the most local quantum dynamics that you can write in this constrained Hilbert space? If you just stare at the problem for some time, you'll soon realize that this is it. So imagine that you have 3 consecutive spins, and this spin and this spin is down or in a Rydberg vacuum. Then you can easily realize that this middle spin can be happily up or down. Okay, and this middle spin being up or down is just like a sigma x operator for spin half systems, right? So that's your minimal dynamics. But of course, you need this spin to be down and this spin to be down. Imagine that this spin is up, for example. Then, of course, this is up and this is up and this is not allowed. Imagine that this is up, right? Then even though this configuration is allowed, you cannot turn this spin up, right? Because then you'll get 2 ups, right? So that's not possible. So this is your minimal model, which is the most local model that you can write down. And these are just some projection operators, which are like 1 minus sigma z by 2 or something, right? So this is like an interacting spin theory in 1 dimension, right? Because if you expand out everything, there are spin-spin interactions here. So now, in this model, if you start with your Z2 state, which is up, down, up, down, up, down, that's your initial state, and you just let it evolve, and you look at the return probability of the many-body wave function, right? So this f of t is basically the overlap of the many-body wave function with the Z2 state mod square. If you just look at that quantity, of course, it starts with 1, and then it decays to 0 very quickly, but then there's a non-trivial revival, there's a non-trivial revival again, and so on. Eventually, this oscillations damp down. That's because in the PXP model, the scars, whatever they are, which I haven't defined yet, are approximate and not exact. But yeah, but still you see on the natural timescales of the model, so imagine that you said W to 1. So on natural timescales of the model, there are rather non-trivial revival effects till a rather long time. Okay, good. However, if you in the same model started with the 0, 0, 0 state, the fidelity would just look like this. It'll just follow this line. go to 0 and just stay 0. I haven't shown this here because, I mean, if I showed it to you here, you wouldn't even see that, but it's basically just this, okay? Right, good, and that's how most of the initial states in fact behave. The fidelity just exponentially crashes to 0 and stays 0, right? But for some initial states, this very peculiar thing happens. Good. So if you look at all the eigenstates of a finite system, let's say by exact diagonalization, and decide to probe some local quantity, let's say the total SZ or total sigma Z of this spin chain, this in their notation is Z1, then you actually see that so this is a color map. So basically these warm colors indicate that the density of states is maximum here. So you see that most of the eigenstates seem to satisfy ETH because they basically stick towards the canonical curve, okay, right? But there are certain anomalous states which are very far from this thermal answer, okay? They're indicated by these crosses, okay? And so these are these quantum scars which are embedded in this otherwise ETH satisfying spectrum, but they strongly violate ETH. And the reason the Z2 state is special is because if you plot the overlap of this Z2 state with the eigenstates of the theory, the Z2 state seems to have a rather high overlap with these scars, okay? And that explains why it has this anomalous behavior and anomalous thermalization, okay? And there are various ways of understanding these scars by now. And even though the thing is mostly understood, but there are still some non-trivial questions which remain in this scarring story, okay? But we won't discuss that here. So I'd like to focus on another aspect of the PXP model here, which is the following. So if you take the PXP model, so one thing you notice here, spectrum is symmetric about E and minus E, okay? For every eigenstate at many-body eigenstate at energy E, there is a corresponding many-body state at minus E, okay? That is easy to figure out why it happens in the PXP model, because there's a chirality operator, which is just the product of these sigma Z operators. So this product, which anti-commutes with your PXP Hamiltonian. Because it anti-commutes with your PXP Hamiltonian, if you take any many-body eigenstate with energy E, you hit it with this chirality operator, that must have a negative energy with respect to this state, okay? But there's another interesting thing. If you look at, let's say again, you do ED and you collect your energies and you just plot the density of states. Of course, the density of states is an even function of E, but it has this delta function piece at E equal to 0, right? Now, why is that? That's because of a certain index theorem, which says the following, that if both your Hamiltonian and your chirality operator commute with a certain spatial inversion operator in your theory, or rather, in general, with some specific point group operator in your theory, right? So here here in the PXP model, it happens to be an inversion operator. So of course, the Hamiltonian will commute with the inversion operator because I'm claiming that's a symmetry of the theory. But I want the chirality operator also to commute with this inversion operator. If both of these things happen together, then you can prove that the number of exact zero modes in a finite system is bounded by the square root of the Hilbert space dimension of your theory, okay? So of course, this number also grows exponentially fast, okay? Even though this system is interacting. Good. Okay. So now we can ask what is the nature of these zero modes and is there anything interesting? So the rest of the story will hover around how to use these zero modes and build certain interesting linear superpositions of these zero modes which violate ETH, okay? So that's the bottom line. Okay, so basically now we think a bit more generally. This is not restricted to the PXP model. There's a bit more general than that. Imagine that you have some mother point. So in the PXP case, the mother point is the PXP model itself. So imagine you have some mother point in some parameter space of whatever theory you're looking at, where there is this exponentially large null space or the space of zero modes, which is protected by this index theorem. Now you can ask what is the nature of these zero modes. let's say you assume ETH. If you assume ETH, then you know that these are absolutely mid-spectrum states. Because they're mid-spectrum states, they are infinite temperature states. Because they're infinite temperature states, locally they should be featureless, right? Good. So a typical zero mode, well, from ETH you expect that any zero mode would actually be completely featureless if you look at it locally, okay? Good. But now you imagine that you turn on some extra coupling in your theory, which is this, right? And such that this coupling breaks the index theorem, okay? So if you're at lambda equal to 0, which is the mother point, which is in general some highly interacting theory, then there is some complicated unitary transformation. It's complicated because, of course, it's a interacting theory, but nonetheless, there is some complicated unitary transformation which exists through which you can block diagonalize your Hamiltonian into a space of zero modes and a space of non-zero modes, okay? The space of zero modes is exponentially large. The space of non-zero modes is a bigger exponentially large thing, okay? But both are exponentially large in the number of degrees of freedom that you have, okay? Good. And as I said, you would expect that these zero modes are completely featureless from ETH. Now you turn on this lambda term. When you turn this lambda term on, then your index theorem is lost. So you would expect the zero modes to hybridize with the non-zero modes, right? But it turns out that if you choose these operators O1 or O2 or O3 carefully, and I'll come to very reasonable choices for these operators, then you can actually show that while most of the zero modes hybridize with the non-zero modes, certain special zero modes remain as eigenstates of the full theory at any lambda. And that basically happened because these are by construction zero modes of your T term, right? So in this notation, the T term has a null space, whatever that T might be, right? And they're also eigenstates of this O term, right? So they're simultaneous eigenstates of this T and this O, even though T and O don't commute with each other, right? And of course, then you can ask various questions. How does the number of these special modes scale? Now, why do I call them special? I'll soon show that these anomalous zero modes strongly violate the ETH, okay? So this is almost like an order by disorder mechanism, but in the Hilbert space, in the sense that you start with some exponentially large number of zero modes, and most of them are completely thermal and featureless. In fact, they live at infinite temperature. There are some special directions which are actually much more structured than a typical zero mode. And the way you sort of glean out those special directions is you turn on a second coupling in your theory, which breaks the index theorem. So it lists this exponential degeneracy. So everything mixes with everything. But these special subset survives as eigenstates of the full theory at any finite lambda. Okay, good. Okay, so in particular, I'll first focus on this nice model where this can be shown. This is just one particular model which I'm discussing today because you can show many things here analytically, but the story is more general, okay? So this is this so-called quantum link model. And again, to people who sort of think about quantum magnetism, this is also the model which comes in spin ice, if you study spin ice. So again, the degrees of freedom here are spin half degrees of freedom, but they live on bonds, if you wish, not on sites, okay? And for concreteness, I have periodic boundary conditions in both directions. So you can just think of ladders now with Lx and Ly dimensions, okay? So now, each of these fluxes can be in or out. And the rule here is that at each vertex, there are 2 in arrows and 2 out arrows. Okay, so that's this ice rule, which is well known in spin ice physics and also in water ice physics. Okay, so this is again a constrained Hilbert space, just like the PXP model, because I cannot flip an arrow independently. I have to satisfy this 2 in 2 out rule. So again, you can ask what's the most natural and the most local dynamics that you can think of, which preserves this Hilbert space constraint. And the answer is known. Basically, you just go to each plaquette here, right? And if you see a plaquette where the arrows go either in a clockwise or in an anti-clockwise direction, you just take the clockwise circulation and make it anti-clockwise. You just take the anti-clockwise circulation and make it clockwise. That's like some benzene move. And then it's easy to see that these moves respect your Hilbert space constraint. Okay, so that's the most local quantum dynamics that you can write here. In fact, the Hamiltonian that we want to write here is, let's say, so it's clear that the Hamiltonian is written at the level of plaquettes here, and now there are two terms here, the sum of all these kinetic terms. So again, I would like to remind you that a kinetic term just locally takes a clockwise plaquette and makes it anti-clockwise and vice versa. And if there's some plaquette where the circulation is neither clockwise nor anti-clockwise, this O kinetic just annihilates it. That's the Hamiltonian. So it's the sum of all these terms, okay? And now, for fun, you can also add a potential term here. So this is a well-known model. This is the Rorschach-Wilson model in the literature of quantum link models and also quantum dynamo models. So what is the Rorschach-Wilson term here? You just take each such plaquette again. Now this is a diagonal term. This was an off-diagonal term in this basis. So here you take each such term, and this is like a counting term. Whenever you see a clockwise flippable plaquette or an anti-clockwise flippable plaquette, you just count it as one. Okay, so that's what these two things are doing. And if some plaquette is neither clockwise flippable or anti-clockwise flippable, this guy contributes a 0. So that's this diagonal operator. Okay, good. So now, here, if you switch off this lambda, usually here in the RK Hamiltonian, Rorschach-Wilson Hamiltonian, you know, people are very interested in how the ground state phase diagram looks as a function of lambda in various dimensions. There are various interesting solid and quantum spin liquid orders which you can stabilize depending on the geometry of the lattice you have. Here, I'm just concentrating on this particular geometry. Okay. So here, if you switch off this lambda equal to 0, then this is actually your mother point, okay, this theory itself. So this theory is a highly interacting theory. So it has a space of 0 modes. And so that's this schematic. This is the null space of this operator, right? And basically a typical 0 mode in this null space is completely featureless. But now it turns out, and this is what I've shown schematically, it turns out that there are actually 0 modes here, which are actually eigenstates of, let's say, this second operator. So these blue arrows. So all of these blue arrows I'll show later on violate ETH. Okay. In fact, one can take a second Hamiltonian, and if I have time, I'll also discuss that. This is, by some abuse of notation, I call it the staggered Rorschach-Wilson Hamiltonian, because you see there's a staggering term here, right? There's a bipartite lattice, so there's a natural staggering term here, right? So you can in fact show that this stabilizes a completely different set of 0 modes which are anomalous here. So the point is that there is this exponentially large soup of 0 modes, and there are all these hidden directions. You want to see these hidden directions, which are these quantum scars. So in one case, you just take this Hamiltonian. This is like this operator O1, if you wish, that I was talking about. It stabilizes one set of these 0 modes. In the other case, this is like this operator O2 that I was talking about. It stabilizes a completely different set of 0 modes, which are all anomalous. Okay, good. Okay, and anyway, this model is very well known, anyway, the ground state of this model on various lattices has been studied for several years, okay, and there's a lot of beautiful physics here. In fact, one of the realizations of a 3D quantum spin liquid, which is the XXZ model on a particular lattice, if you look at just the low energy effective Hamiltonian of that spin liquid, is just this Rorschach-Wilson Hamiltonian on another particular lattice, but with lambda equal to 0, exactly equal to 0. Okay, so anyway, so there's a lot of interesting stuff here in the ground state as well, but we are concentrating on high energy now. So now I'll rush through a bit because I want to leave some time for questions as well. So anyway, you can prove that the index theorem here is satisfied for this model at lambda equal to 0. You can prove that. And there's just a numerical demonstration of this. If you take lambda equal to 0 and you take finite ladders like maybe 10, 2, so this is Lx and this is Ly. This is Lx and this is Ly. So there's a slightly wider ladder, 6, 4. And you again do exact diagonalization because of course there's a highly non-integrable theory, so you cannot solve the spectrum exactly. You see just from your ED data that there's this giant weight of 0 modes up till machine precision, right? That's just happening because of this index theorem. Okay, good. And so now if you turn on the lambda here, as I said, that there are certain anomalous zero modes which are simultaneous eigenmodes of both the kinetic term and the potential term of your theory, right? Or the kinetic Rorschach-Wilson term and the potential Rorschach-Wilson term. So they are eigenstates of the theory at any lambda. They stay unchanged with lambda. Okay. So now let's say I focus on one particular energy, some particular energy. This energy is special. I'll come to it very soon, why it's special. Now you span all initial states which have exactly this energy, okay, for some particular ladder. So this turns out to be 14,2, okay. So then it's an enumeration problem. It just so happens that there are 6,433 initial states exactly with this energy. So basically, if you believe ETH, all these initial states, if you just let them go, should thermalize. That's exactly what's happening here. This is one initial state, this is another initial state, there's some local operator, doesn't matter what it is, some local operator. You see, its value is very different for this initial state and very different for this initial state at time t equal to 0. But soon, you see, they just go to the same number. That's the hallmark of thermalization. And they go to the same number because they have the same energy, right? So they're controlled by the same temperature. But there are 18 initial states exactly with this energy, which has a rather big overlap with these anomalous zero modes that I talked about, with these special directions that I talked about. There are 18 of them. So if I show any one of them, you see that it seems to thermalize, but it just goes to the wrong number in this finite system. That's because it has a rather strong overlap with one or more of these anomalous zero modes. Okay, good. So clearly there's this memory effect in the unitary dynamics as well. Okay, so why are these zero modes anomalous? The argument is very simple. So suppose you take the Rorschach-Wilson model. This is a non-integrable theory. So if you are at some coupling lambda 1 and you change your coupling to lambda 2, so let's say you just change it by a small number. If you look at the high energy part of your spectrum, where there's an exponentially large number of eigenstates packed close to each other, so that there's a finite entropy also if you want to constrain the theory, then of course if you perturb the theory a bit, you know, all these high energy states completely change their nature, right? So if you expand any high energy state here in this basis, it looks like a random state. In fact, that's the hallmark of a random matrix theory, right? That's why I've just used two different colors. There's an artist's impression to show that these states are completely different from these states. But those anomalous zero modes, as I said, are eigenstates of your theory for any lambda. So these anomalous zero modes, which are indicated by these blue lines, stay completely unchanged. So they violate random matrix theory and hence ETH. That's it. So this is the argument why these anomalous zero modes violate ETH. Okay. In fact, there's a lot of variety in these anomalous zero modes, which you can read about in this paper. In fact, the way of looking at them is through the mother point again and categorizing them in terms of zero modes of the mother point and non-zero modes of the mother point. So there's an entire classification there and all the things that you can imagine will happen here. But anyway, so yeah. So now let me focus in the remaining 7 minutes or so that I have some time for questions on this particular sublattice cars in the quantum link model. So these are anomalous zero modes which are highly structured if you consider one particular local operator. Remember, there was this potential operator, which was just a counting operator on a single plaquette. So all these sublattice cars have one property, which is that if you go on the square lattice, which is a bipartite lattice, and you look at any of these eigenstates, this O potential is uniquely 0 on one sublattice and uniquely 1 on the other sublattice. So with respect to this operator, this is the most structured state that you can write, because O potential as an operator has a minimum value of 0 and a maximum value of 1, right? So this is the most structured object that you can write if you just look at this local operator. So clearly all these states violate ETH, right? Because a general infinite temperature state would just have O potential equal to 1/2 at this plaquette, 1/2 at this plaquette, 1/2 at every other plaquette, just by symmetry, because it's an infinite temperature state, okay? Good. And all these sublattice cars either have zero energy with respect to O kinetic, which means that they live in the null space of O kinetic, or in fact, very interestingly, they can even have integer values with respect to O kinetic, which means that they live outside the null space of O kinetic. I'll later show that there's a very interesting triangle relation here. We just figured out this relation numerically, and I'll state the relation to you. It's very easy to state, but it's extremely hard to understand. So if somebody has any clever idea of how to prove it analytically, please eliminate me later, okay? Good. So as I already said in words, all these scars have this property, which evidently already shows that they violate ETH, right? Because they are highly structured with respect to this local operator. Good. So now we can have an analytic construction of a subset of these short singlet scars, excluding questions, right? Yeah. Subset of these sublattice scars in the following way. So let's look at the most local problem now. So this blue is an anti-clockwise circulation, and this red is a clockwise circulation. So if this guy is clockwise and this guy is anti-clockwise, you can necessarily show that this placket is unflippable and this placket is unflippable, no matter what the arrows are here. I have left them unspecified. So you hit this with O-kinetic, you will, so this is a class of sublattice scars. This doesn't exhaust everything. So you see, if I hit this with O-kinetic, it's very easy to see that you will get this, right? So the colors just indicate flippability here, right? Now I haven't written UU here because in principle, some of them can turn flippable. And if you hit O-kinetic on the reverse of this, you get this. So now if you put a singlet sign structure here, locally, these two things just cancel out. These four terms cancel out. So this singlet, this emergent singlet, is actually a zero mode of this O-kinetic term locally. Now the question is, this is a very local argument. Can you pack it on the entire lattice? In fact, you can pack it. It just becomes a dimer problem with not one but two dimer constraints. There are a set of green dimers here which cannot touch each other on this dual lattice. And there are a set of perpendicular blue dimers here, which again cannot touch each other on this lattice. And just by these dimer rules, you can write all the short singlet sublattice scars here. All of them have O potential to be n placket by 2, where n placket is the total number of plackets in your lattice. And all of them are by construction zero modes of the O-kinetic operator, because this is just a tiling problem. So I've solved the tiling problem. That's it. So there are nice counting things you can do here. And so for a thin strip of Lx comma 2, you can prove that there are only 4 such sublattice scars. For a slightly thicker strip, you can prove that there are exponentially many such sublattice scars. And okay, anyway, so these are lower bounds, because as I said, the singlet sublattice scars don't exhaust the full space of sublattice scars. Right. So now let me quickly go to something else which I want to show. There are many other sublattice scars which we can figure out by a clever numerical construction which goes beyond exact diagonalization, because there are system sizes here which you simply cannot access through ED. So this pseudo exact diagonalization just focuses on the correct Hilbert space of the theory and not on everything else. But anyway, I don't have time to explain that. So let me show you an example of a non-singlet sublattice scar. These states are very interesting. We don't understand them completely. See, so one property of the singlet sublattice scars is whatever you do, there must be an equal number of blue and red dots in your thing, because a singlet is formed by one blue and one red, right? So, but you see here, these contributing Fock states, for example, this guy has 3 blue and 5 reds, and then there would be 5 blue and 3 reds and all. And these are very structured states which you can write down for various lattices just by observation, but I don't yet have an analytic way to generalize it to infinite lattices. But the key thing here is that there's a very interesting relation of, so let me just come to that relation. There's a very interesting thing here. So as I told you, there are some sublattice scars which, when you hit O-kinetic on them, give you ±2. So they're outside the null space. Now the question is, are these anomalous modes which are outside the null space of O-kinetic related somehow to the anomalous modes in the null space of O-kinetic? So for people who sort of follow quantum scars, this is one of the interesting and open questions in the field. So here it turns out that there's an interesting triangle relation. So the triangle relation is the following. So if you take a state outside the null space and you take its chirality partner, which by definition, so if this state has O-kinetic +2, then chirality C times this state has O-kinetic -2 by definition, because it lives in the negative energy. If you now take the difference of these two states, and hit it by a certain weird operator. What is this weird operator? This weird operator does not have a local representation. So this operator is the following. So you see there are certain Fock states here which have, let's say, 3 blue and 5 red, and there are certain other Fock states here which have 5 blue and 3 red. So if you just take the guys which have 3 blue and 5 red and change their sign, I'll be done in 1 or 2 minutes, and change their sign, but don't change the sign of the other guys. So it's some majority rule that I'm taking, right? So it's clear that I cannot write it locally. I'm just counting the things and taking a difference. Then if you do this sign change for 1/2 of the states, and you do it here, miraculously you get a second state, which is an anomalous zero mode, an anomalous sublattice scar, right? So this gives a connection between the scars outside the null space and the scars within the null space, and 3 states are involved here, so I just call it a triangle relation for the heck of it. Doesn't have a deeper meaning than that. But okay, so if you write a long-range parent Hamiltonian for which these sublattice scars are actually exact ground states, then this relation has an interpretation as a creation of an excited particle when you act this operator O on one of the ground states of this long-range Hamiltonian. But as I already said, this O cannot be written down as a sum of local operators, so it's still a bit weird, but anyway, right? So there are various other things you can do here, but let me just take 1 minute to focus very quickly on what happens if you put disorder here, and then I'll stop. Yeah. So this is some Abelian theory or some interacting theory, right? It's not non-Abelian. So if you put strong disorder here, your naive intuition might tell you that there is MBL here in 1D. Of course, there are lots of debates of whether there is MBL here in 1D or not. But on finite systems, we know how things are different, right? So here in this theory, if you look at weak disorder or strong disorder, look at level statistics, you see they are practically the same. If I didn't give you these labels, you couldn't have distinguished weak disorder from strong disorder here. So the first point is that there is no sign of MBL. The second point is the sublattice scars are stable to all orders in disorder, right? Because they are completely structured with respect to O potential, and you're putting disorder in O potential. You're just making this coupling lambda a function of space, right? So the sublattice scars are still eigenstates of your theory. But the interesting thing is that there seems to be, even though there is no MBL, and so most of the high energy states are completely thermal, if you look at the variance of O potential in real space, so this is the variance of O potential in real space, even though most of the states are completely homogeneous in real space, till a certain disorder, let's say alpha equal to 2 here, if you crank up your disorder, there comes a critical disorder strength, beyond which there's a cascading of new disorder-induced scars, which are different from the sublattice scars. And these new disorder-induced scars are like puddles in real space. They break up into patches. So you can just figure it out by looking at O potential in real space or O kinetic in real space. This is like a typical state, the blue state, right? So this is completely featureless apart from finite size fluctuations, whereas the the disorder-induced scars have a lot of structure, right? So maybe, yeah, that's an interesting thing. I don't know how to explain analytically yet, so maybe I'll leave you with that. And maybe I'll just flash my conclusions here and stop and take some questions if there are any. Yeah.
Questions? Interpreting that only a subset of the zero modes at the mother point is violate ETH?
Yes, that's correct. A typical zero mode would not violate ETH. The subset can exponentially increase with system size, but it's still subdominant compared to the total number of zero modes.
Okay, and is there a general feature of Hamiltonians with such index theorem, or is it special to these Hamiltonians?
No, it's, as far as I believe, it's general. There is no proof, but I can give you various other constructions where this index theorem is satisfied, and all of them show this. So yeah, okay. I believe it's general. There's no proof though. Yeah.
Okay, thanks.
So other questions? Yeah.
To switch on the perturbation, like some of the scar states still survive, right?
Exactly, they're eigenstates of the full theory.
What about the non-zero, which are non-zero mode scar states, they disappear? Is it?
Sometimes they disappear, sometimes they don't. As I said, I mean, for example, you see these scars with O kinetic equal to ±2, which are again sublattice scars. They never disappear. They are always eigenstates even at a finite lambda, but they're outside the null space. But interestingly, there's a connection between these guys and the null space. from this operator rho, which is some weird operator. Yeah, I don't know how to write it in sums of local terms, right? Yeah, so there is some connection. Yeah.
Okay.
And there are other examples, but yeah, due to lack of time, yeah, I didn't show them.
Okay. Are there other? Okay, if there are no other questions, let's thank the speaker once again, and we come back here at 10:30.